The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, a group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Hello everyone, I'm geologist Philip Ong. I'm here with Mr. Dane DuPont. We are here with HawaiiTracker.com, bringing you guys another Kīlauea volcano update. Today we're going to do something a little bit different. We're going to go more quickly over the volcano monitoring signals at the start of our update, and then we're going to do a little bit more of a deeper dive and spend more of our time today on hotspot science, talking about what science is known and show you guys some of the graphics that have been put out about what the hotspot actually is, why it's under Hawaii, where did it come from, how does it connect to plate tectonics, and all those kind of questions. So we'll get to that a little bit later on, but we will start off first with our volcano update. And so we'll start looking at the USGS Hawaiian Volcano Observatory webpage as usual. And we'll take volcano questions here after this first little volcano segment, so make sure to pass them to Dane, and he'll be monitoring the chats and streams to make sure that you guys get your questions answered. We'll start off with the USGS data here, looking at the volcano, and we can see that in the last 2 days since our last update, we've actually had a deflation from 2 microradians down to minus 0.7 or so, maybe. So about a 3 microradian decrease, and then it's come back up since then, about a microradian or so to the point where we are right now. So looking back at this past week graph, let me change my color to make it a little easier. See here? you can see that we came out of our last week's long deflation with a big inflation. That was in the order of 8 microradians or so from top to bottom. That's the amount of tilt that the ground is showing. And our more recent one in the last couple of days is only in the order of from a little over 4 microradians to a little under 2, so maybe 2.5, 3 microradians. Not nearly as big as that increase that we saw just at the end of last week there. So looking back for the past month, I'm going to zoom into this a little bit more here. And there it is. You can kind of see that we had earlier in the month a couple of back-to-back deflation-inflation events. There's a deflation-inflation, there's a deflation and an inflation again. And here we are at the start of February. Big deflation, big inflation, and then a smaller deflation, and it looks like a smaller inflation that's almost back to where it started. So that's our main signal we're looking at here. Correspondingly, the lava level at Kilauea summit had been rising, but it then very slightly went down, and then came back up again, and then very slightly went down again. And so it's kind of mirroring the pattern of the surface pressure, which we're using the tilt of the ground as a proxy for. So that's how the lava levels are measuring. And if we look at the USGS text update, we can see that the number is 214 meters, 702 feet deep for the depth under the west vent of that filling lava lake in Halemaʻumaʻu crater. And that is 1 meter, 3 feet lower than a couple of days ago. And so you can kind of see that's a very slight contraction there, presumably from the gases just bubbling out of the lava and allowing it that extra space as it's kind of denser and gooier, but also occupies less volume. And so then you actually have lava coming in continuously the entire time, but it's also gas poor, and therefore you can still have a filling in and a net level going down. It's going to be something like that. We imagine the dynamics that are actually happening. So otherwise, in the text update, we still have our February 1st measurement of 2,200 tons per day, and we'll just await further information on that. And there's really not a whole lot of new information around there. They are saying that the dimensions of the main island remain unchanged, with its edges 6 meters, 18 feet above the lake surface. So it is doing some moving, perhaps, and adjusting as well. But then there's also the density factor. So, all right. Moving on, we're going to cover the volcano more quickly today. Here's our earthquakes map of Hawaii Island, and we can see our main cluster is down here. That's South Pahala area, where our feeder area for the hotspot, we'll be talking about later today, is thought to connect into the volcanic pile, and from there, there's a branch that goes to Mauna Loa, and a branch that goes to Kīlauea, and a branch that goes to Loihi. Okay, so we're going to be looking below that, beyond that, a little later today. You can see it's still active. That zone of magma supply into that lower crust is still active. Lower crust, upper mantle, even, right? That area right in there, but more rigid rock that actually can break and create earthquakes. And otherwise, there's still a few scattered earthquakes at Mauna Loa summit, but really nothing of note, not at the frequency and intensity we'd expect for any kind of building activity there. Otherwise, Kilauea's south flank has actually been quiet in the last couple of days, as has its summit. So nothing to really speak of there. We do still have VOD coming out of the volcano, but presumably at those lower levels, it's a little bit better. The weather is a little bit back to normal trade wind direction from the northeast, so we do have our regular gas plume to the southwest in the areas of Ocean View and Pahala, and wrapping around into the Kona areas to some degree as well. So if we look at our purple air map, which never likes to load when I switch to it here. It's showing in North Kona mostly greens, but a little bit of air effects, especially down here in South Kona, whereas our ocean view stations are actually looking pretty good today. So that is the gas. If we look at the webcams. Here's a view from the KW cam, USGS HVO webcam. This is their automatic 24-hour time lapse for the last days. You can a lot of gas coming from the west vent right underneath here, and it's putting lava at its base into this filling lava lake, which is about that size, with this big island in the middle of it, which maybe is kind of blocking off and really turning it more into a kidney bean kind of shape now, especially as the lava levels have been lower. It's receded from these upper areas around, as we've indicated in our last update. So we can look at the view from the south, SW view. That previous view was from the upper west, looking down this direction. Now we will look up here and see our west vent coming in and filling that kidney bean shape, something like that, from this angle, with that main big island.
We have a $20 super chat from Scott Hartman on YouTube. No comment. Thank you, buddy.
Mahalo, mahalo. So that's the view from the S1 cam. You can kind of see this. You don't see a whole lot of change. A little bit of on and off lapping in this northern and southern areas, kind of where it's coming, flowing on that edge around over there, but it hasn't really gone back up there since that last high peak of inflation. So we'll switch to our thermal camera, and you kind of see the same thing. We're now looking back from the west, off in this direction. So our previous view was from that direction. And now we see our island broadside, and we see the kind of kidney bean shape more obvious in the thermal camera right there. Then kind of this is the shoreline, so to speak, where the lava is lapping on. Right when it rises up, it'll come up into these areas, into these kind of bays and shallows, and then when it's draining, it's going back down those same areas, whereas this closer in area seems to be constantly churning. We haven't seen it freeze all the way for a while since the very last deflation, big deflation event. That was, yeah, not quite a month ago, a few weeks ago. So that's all there is. And I can kind of see that there's still some islands floating in here. There's not a whole lot of other action. You can see the pressure coming up does allow these squeeze ups in the back part of the crater to continue. And most of the islands are submerged at this point, right? We don't see all those small chunks. We see kind of that one, and we see that one. And they're actually fairly big. And so we'll look at the USGS imagery, and we'll go from the oldest to the newest imagery here. So we have February 4th. After a heavy rainfall, seeing all the water flash to steam, and quite a lot of steam all around the crater. Looking down in here over the lava lake, February 4th. So not quite a week ago, but almost. Then February 5th. This is during that low point in our deflation still. So what you can see a little bit different is you can see all these islands emerged out of the lava lake during that time, as the lava level was not only lower, but presumably the gas content was also lower. So it was sitting lower, and these little islands were floating higher, so to speak. Right? And there's the west vent, and the edge of that perched lava pond, which now has a little down drop cliff. Kind of see a little ledge right there, right, showing the lava level has gone down. So that is the view you can see here, and a little bit here on the right side of the shoreline, so to speak, where it kind of comes and flows up onto that ledge. And presumably it's going under that ledge as well to be able to squeeze up on that outer crack from time to time. Okay, so that's February 5th. And this is a close-up view on Friday, February 5th as well, of one of those smaller islands on the eastern side of the lake. What they're showing here is a smaller rock fall off of the side. So it's interesting. Maybe I'll click on that one so you can get a little bit better resolution than I see on my screen here. Because what you can see is that the outer edge of the lava, let's go all the way in. So I'm scrolling down and clicking in the original, and lets me zoom way in. So you can see here the outer veneer of that lava. You can kind of see a cross section right here. There's like a layer of lava on the outside, kind of coating what you can see is red baked cinder on the inside. So it's being heated by the lava. and essentially that's oxidizing it. The iron is rusting, the presence of the heat mostly, and so everything's getting baked inside of there. So the veneer on the outside kind of collapsed down onto that solid lake surface. You can get the inside exposed, get a nice little cross section. See right there what these islands are kind of made of, right? So as we have been speculating and anticipating, a lot of cinder in there. And so let me go back and go back, and we can see that there's a zoomed in view section of the western lava lake here when it's still showing crustal foundering. The crust turning over February 5th. Close up of the lava stream in the inlet. And so here you see some of those bigger chunks sitting above the lava level, coming from the west vent, which is up here. And it's flowing down in here. And this is during that relatively sluggish, with a reduction in lake activity and a deflation cycle. Kind of similar view here again. And I'll keep going up here. They've actually, this one might be worth looking at in a little more detail. This is the terracing that we've been discussing in the past few updates. You can kind of see almost like natural contour lines of different overflow levels, because the lava has been flowing out of that pond, but it's been receding in the meantime. So you see every layer goes a little bit less far, and it goes a little bit higher, and so it leaves this pattern you can kind of see across this whole side of the island. This is that big island. There's the ledge of how far the lava is liquid still underneath, and it's dropped down. And you can kind of see on the surface this terracing pattern there, and all the way like that, all the way around. Interesting stuff there. And then we have a view of the west vent up here, similar to our webcam view. There's our stagnant eastern portion. There's not a whole lot new there. And that was the update that was put out yesterday. So looking at the update today, we have another picture, different angle of the lava lake. The features aren't really changing a whole lot now. You know, it's kind of receded back to this lower part here. And here's our kind of shallows here and here. Not a lot we can really see there, and it's any different. And another aerial view over here, maybe a little easier to see the shape of active lava in here. Something like that. Although there's a branch in here, a branch in here. It's not quite clear. And a zoomed in view of the active west vent is over here. Putting out gas. And lava coming out of the base hasn't stopped. Although in this view, here on February 9th, you can kind of see that we actually have some of this gassy or presumably lava is lapping up onto this island and giving it another coat. And so it's getting more, it's not only more submerged, it's having lava actually came up and onto it. Possibly before it receded a little bit again, right? With the deflation-inflation following back to back. Okay, so that was February 9th. And that is imagery for the volcano. And that is the abbreviated volcano update for today. There's really not a whole lot of change. And everything is kind of as we've anticipated. So we'll take some questions on the volcano now before we turn to our hotspot science segment.
All right. Well, we do got to thank HawaiiTracker.com for helping us be able to bring you this presentation. HawaiiTracker.com is a community-based social media site, a little bit different than many of the social media sites that you're used to. We have more of a community focus and local area. So we are on HawaiiTracker.com. Best way you can support us is to share this video. We don't have advertising like many of the other media organizations. So we rely on people like you, our viewers, to share this video, like this video, help it get trending in the algorithms. And then secondly, to go to hawaiitracker.com, become a member there, become a user, help interact and build our community. Third way is monetary support. We do take donations on hawaiitracker.com/support. And we appreciate everybody that has donated through that. We do have a few new donators, Lisa J and Mel S with a monthly donation, and we appreciate all those. All right, with that, we don't have that many questions in the beginning section. There are some questions pertaining to the hotspot, but I figure we'll get to those after you do the presentation. So as to the activity right now, Dark Zones asks, does the inflation directly affect the amount of lava coming in? Does it reflect that direct correlation?
What we were seeing before was a correlation with a tremor, and a tremor isn't exactly only the amount of lava coming out, but it could also reflect the gassiness. And so that's something we're more relying on the visual observations of the USGS scientists. And they're the ones reporting that they've seen continuous flow and no starting like they have reported in the past. So that's the main observation there. It does seem the kind of lava coming out may be less gassy, like I said, and that could be reflected by that lower level relative to the islands, and also that kind of receding aspect of the surface of the lake. So that's as much as we really know there. It could affect it a little more, but it's hard to really tell. And the tremors, the vibrations that we talk about are probably more like the gas bubbles possibly moving through those conduits, like kind of high pressure, low pressure, high pressure, low pressure, kind of going through, that creates a vibration, more so than the less gassy stuff. So it might be harder to detect, and that we don't have the right instruments that I know. The tilt really isn't sensitive enough, right? And we have second to second the amplitude of tremor, and that's kind of why I think of that as a next possible thing to look at.
All right.
Yeah, and beyond that, we'll wait for USGS to chime in and give us the real scoop.
A question of, is it possible to determine the surface temperature of the seemingly solidified area of the lava lake?
That's tricky. I'm not sure that I'm the right expert to consult on that, right? We've kind of talked about how on lava flows you've seen crust that's a few minutes old, that's already like in the hundreds of degrees rather than over 1,000, just because of that kind of insulating effect. We've seen a picture of that rockfall today that didn't break the crust or squeeze up any lava out of the crack anywhere nearby there, right? We kind of see in this thermal that while lava is popping up from the edges, only one time did it pop up out of the spot in the middle. And mostly this whole thing moves as a giant solid lid. And for that to happen, it must have some amount of thickness to it, right? And thickness means it's able to insulate better. So it's hard to really say. If we look at this USGS temperature, it's saying it's somewhere between the range of 100 degrees, right? The purplish should be 200. We're not seeing that quite anywhere except on the edges. So that's what the thermal camera says, but it may attenuate over that distance, being as far away as it is.
And we've seen, in some of the lava flows, especially at down Kalapana during those decades, is you would have a very a recent lava flow that came through an area with a cool crust on it, right? Mm-hmm. Cool to the touch. But you could still look down in the cracks of it and see glow from molten stuff a few inches down. And it was just crazy, the transition on that, how fast it dissipated. All right, we do have a question about the crumbling island in the middle of the lava lake. Mm-hmm. Alexander asked, does the red color represent rust content of the cooling rock on the crumbling island?
Yeah, essentially. Yeah, that's exactly. That's what I was trying to say as well. Yeah.
Right.
So this island right here, and and go to this original view. And
He means iron content, yeah.
yeah, so
Does
I
it
mean,
show the iron content, the amount of
yeah.
rust or the coloration?
Yeah, I suppose that what I'm taking for granted is the fact that all of our lava rocks in Hawaii have a lot of iron in them, right? So that's just the kind of rock that we have. Everything is iron rich here. So in Hawaii, I guess for me, I kind of assume that because it's a given, right? But absolutely, our lavas and all our soils, that come from the lava, which is where they come from, combined with the ash and organics, is very iron rich. And so yeah, you do see that. Anything that has a chance to be baked, right, and can alter, things. If you think about rusting, rust happens the fastest when you have a high water content and high heat. And we believe that the cinder was formed in the presence of that pond of summit water, right? And lava was nearby. So you have water, you have heat, you have the iron-rich rock, and got baked, oxidized.
All right. Ed from YouTube asks if it would be possible to crack open an old vent or fissure to explore the inside of a volcano versus the surface of a lava tube. So maybe what would, if we dove down under the rubble of Fissure 8, what could we expect to find in the first few hundred feet, first 20 feet, and way down like a mile?
Yeah, it's a great question, and I think we all wish we knew. I think the most exciting thing that I've heard recently, was last year's Volcano Awareness Month. There was a field trip led by Carolyn Parchetta, and she'd developed this little robot that could crawl down the crack of the fissure and map it out in 3D. And so she could lower it down as far as it could go in the crack. It could basically make a 3D map. And so the crack doesn't have to be big enough for a person to get into, as long as this little crack-shaped machine could crawl in there. It could measure all that stuff, right? So that's
interesting. Yeah.
Yeah, go ahead.
One of the things that immediately reminds me of is the guys in Leilani Estates following the eruption that happened to have the fissure line come across, and still the property is still mostly there. Just the amount of change that they've been able to see in that area with the cracks over time, and just how it's developed. But one of the things they did immediately after the eruption was they wanted to know how deep it was, right? So one of them hooked up a string and had marked the string and jiggled the string down with a weight and tried to get it down that way, right? Another one just threw a glow stick down the crack to see how far he could get it, and both of them were saying it's incredibly hard to get it down there without getting hung up on some artificial ledge or just superficial ledge or some hiccup on something. But yeah, it's a lot of curiosity on that, even from people that went through the eruption. It's like, hey, how deep does this crack now go?
Yeah, I mean, what happens in fissures especially is that the lava would drain back into the crack as the eruption wanes, and that kind of plugs it up, right? And sometimes that lava plug will kind of get burnt back out, as we saw with Fissure 8. It actually drained in and filled in, and then it kind of popped back out again for a few days, and it drained back in and collapsed finally after all that was said and done.
Right. So we do have one more question here.
Let me just say also, I mean, there is I think there's a place in I want to say it's in Iceland, right? That there's inside of a volcano you can go and visit an old magma chamber. So that's kind of thing, but it's not here in Hawaii.
Yeah, for sure. Just checking to see if there's any new questions that I missed since we started this. Dave asks if the lava is still fluid under the entire lake. It looks like the welling up at times around the eastern rim.
Yeah, exactly. Yeah, I imagine so as well. I imagine that it probably is fluid under the whole lake because of that eastern rim, which is just a second. That's right over here. Section right in here, and over here as well. I kind of wonder, that's the kind of thing where if we had access to this, I'd love to have a sample of this kind of lava compared to this kind of lava. Be able to tell if this thing's been sitting around and it's kind of gooier stuff that's just getting pushed over, or if there's a full-blown circulation under the whole thing. That's kind of what I'm curious, right? Like, how thick does this thing go down, right? I don't expect it's that thick, but how gooey is the lava underneath it, and how resistant is it to flow? Is it kind of piled up in one big glob over here? Or is that glob kind of lower down in a crater? Is there an upper shallow area? I imagine there's probably some layering going on in there, right? I think when we talk about the hotspot later, we can kind of use this as an analog, right? This is like a crust of the Earth that's kind of floating on this hotter mantle material below there, right? And you have a kind of crust that forms, and it can move around, and stuff can squeeze out to the edges, but there's a whole bunch of different layers with different properties that occur underneath that upper layer of crust. Maybe what actually is going on. Kind of a curiosity there. So maybe with that, I can transition to the hotspot science. Anything else, Dane?
No, that does it for the questions for this segment. I'll be saving some of the hotspot specific questions for the next segment of question and answer. And back to you.
All right. Mahalo, Dane. Mahalo for those questions, you guys. All right, so we're going to do a little review on Hawaii volcanoes, and we're going to kind of start with this most zoomed in view, and we're going to zoom out kind of from here. But kind of to cover one of the more basic questions that we often get is, what are the volcanoes that make up Hawaii Island, right? And so Hawaii Island has the 5 volcanoes that are on land. Kīlauea, I'll kind of outline their shapes, something like that. It's Kilauea. Mauna Loa, which is everything on this side of Kilauea, all the way up to in there, and all the way to North Kona, and it goes around Hualalai, and then South Kona, and all the way back over here. That's all Mauna Loa. It last erupted in 1984. Kilauea, of course, is active today. We have to our far west, Hualalai, last eruption in 1801. That's only popping up in this area right over here. This lava flow over here is the one from Hualalai. That's a more recent one. Mauna Kea is 4,500 years ago was the last eruption. It kind of comes up something like this. And Kohala, 120,000 years ago, is the last volcano that makes up Hawaii Island. And so a geologist will call a volcano active if the volcano erupted in the last 10,000 years. We've kind of mentioned that before. So here we are. This volcano is not active, and it may be called extinct. Extinct not meaning that it will never erupt again, but that its main magma pathways are not the regular. The first phase of young eruption is over, right? And it may rejuvenate in a younger eruption, but it's out of its active phase. Mauna Kea we'd call active but dormant 4,500 years ago. Hualalai active for sure, 219 years. Mauna Loa a little bit less than that, active and dormant. Kilauea active and erupting. To our south we have Lo'ihi. 1996 was its last confirmed eruption by submarine. And it's had magma movements for sure, but last eruption was 96. And off to our northwest, submerged in the ocean, is Mahukona volcano, which was thought to have erupted 470,000 years ago or so. All right, so that one long since extinct, right? Okay, so we'll move on. We can kind of take this view from University of Hawaii, Manoa, School of Earth Sciences, and we can imagine what the mantle plume, or this kind of hotspot, as it's often called, is coming up underneath Mauna Loa volcano, Kilauea volcano, and Lo'ihi volcano right here. Right, so somewhere in an area that kind of encompasses all 3 of those summits of those volcanoes is this area coming up. Now, why do I have it labeled mantle plume and not hotspot? Because there's been some debate about how hot is that material, and how accurate is it to think of it as only as a hot material rather than a plume of some kind, of some mixed hot and other property material. So within the geological community, it's a little more accurate to say mantle plume, but I certainly understand when you guys say hotspot, this is what you're talking about, and we won't get too picky. So we have the Pacific Ocean crust moving to the northwest, about 4 inches a year, kind of in that direction, and that's why we have this trail of other islands off in that direction. It's often portrayed that the mantle plume, the hotspot, is stationary in one spot, and if we kind of start off with that more simple assumption, you can kind of see that the moving ocean crust would leave a trail of other islands behind it. You can kind of see that in this first view here. All right, so we'll zoom out a little bit more. And here we have Hawaii Island, which has an age next to it here, 0.7 million years to present, right, where the hotspot currently sits underneath. And what exactly is a hotspot? A mantle plume. It's a hypothetical hot, narrow mantle upwelling that has unique physical and chemical characteristics. So when we say hot, how hot is it actually? Because everything down there is hot. This zone right in here may be at 1450 Celsius or 2650 Fahrenheit, right? Only 150 degrees Celsius or 300 degrees Fahrenheit hotter than the surrounding material, which is also quite hot at 1300 Celsius or 2350 Fahrenheit. And we're talking about, this is all underneath the lithosphere, right? So you may have heard of me say a few terms so far. I've talked about the crust. That's this upper section in here. And the upper mantle is from there to there. And together they form the lithosphere, litho meaning rock. And so this is the kind of the behaving as a rock part of the Earth, right? That the upper mantle, that's still solid, and the whole crust of the Earth together, the lithosphere. And so the whole thing altogether may be in the order of 50 to 75 miles down, 820 kilometers down. And this is obviously a variable thing. It varies from place to place. It's an area of active research, and we really don't know what this looks like in here. This is just one Wikimedia Commons image that kind of shows what we're dealing with here, right? And so we kind of have off to our northwest, Maui at less than 1 million year old, Molokai from 1.3 to 1.8, Oahu 2.2 to 2.3, Hawaii at 3.8 to 5.6, progressively older to the northwest. And that pattern is evident also on a globe. Here's our big island of Hawaii, and the Hawaiian chain goes to the northwest here, and then where it takes this bend from that point upwards, and it's all submerged, is called the Emperor Seamountain chain. So combined, that's the Hawaiian-Emperor Archipelago. Right, this is a whole northern part over here submerged. Okay, so we're talking about this zone below the solid part of the Earth, right? This lithosphere that's overlain by the ocean. And from that hotspot, there's different feeders to different volcanoes. And there's one to Loihi, there's one to Kīlauea, and there would presumably be one kind of back in here to Mauna Loa, right? So that zone of deep earthquakes is in this zone right in here, this upper part of this feeder. And that's where it's kind of connecting into the volcanoes, but we're going to zoom back out from there and see where this actual thing comes from. And first we're going to kind of just review how this actually happens. So there is our hotspot down here in the more fluid mantle. And one thing you might notice is that it's injecting feeders into each volcano. And as the plate moves to the northwest, you can see an island of different volcanoes form here on the surface. And you kind of see that the feeders kind of get carried along with the crust. And so you can actually have lava that's entrained in a volcano that's not directly over the hotspot still. And the volcanoes kind of take a while to die off for that, right? You can also see a little bit of this bend. The crust actually bends downwards from the weight of these islands over this more fluid lower medium of the mantle. And the other thing you can see is as the plate moves, this plume kind of gets dragged along with it, right? So it kind of wants to move over in a direction of plate direction as well. This is a simple graphic. This is from Iris. I should Iris that /earthquake right here. So you have some great animations and educational tools. So that is the hotspot track. And now we'll kind of zoom out a little bit more and we'll kind of see that that whole area we're looking at was down in here. And we can kind of see that we have French Frigate Shoals at 12.4 million years, Midway Atoll at 28.3, Daikakuji 47 million years, right at that bend. And for those of you curious about this bend, we will get to this. It's going to take a while to figure out all the components to let us answer the question of why is there a big bend in this archipelago right here, which is something we'll certainly address. We have Koko at 49 million years, Toko, Suiko, 56, 61, and all the way up here, Detroit Seamount at 80 million years old. Meiji, possibly around 85. Some of the dating is a little suspect, but that's the ballpark of what we're talking about here. And so I can kind of zoom into, maybe, I don't know if I can or not, but if you superimpose that on a map of the continent of North America, you kind of see that if we put the Big Island at the southern tip of Florida, that spans a distance all the way onto the main land of Alaska past that panhandle. So it's a very, very long, huge feature on the surface of the Earth. It's a major feature that has geologists from the whole world researching, and so we have quite a lot of researchers from all over asking questions about this, like why is there a bend? And some things you might notice is where is the start of this thing? There's a big boundary right here where it may have been consumed already by the subduction process of the Earth, but where could it have gone? You might say, why does it look like much more continuous a line over here? And then it seems like it stops and it starts and it stops and it starts. And then why does it seem like it's very weak for long periods of time? And then maybe more recently it's been more strong, producing more landmass underwater. So all interesting questions. And as the hotspots stays relatively in the same spot and the plate moves away from it, those northwestern islands over time will sink into atolls, right, in this classic process. So this is the volcanic island phase, and then this is the next 2 to 5 million years as the island sinks and erodes and the reef grows around it. And eventually after 5 to 10 and 10 to 30 million years, you have an atoll kind of formed over it before the whole thing kind of submerges even too deep for a shallow reef to grow on it. And so that's what we have, or some of our 80 million year old seamounts are way past this stage. But it's important to realize this process when you're trying to study this feature. So what scientists have done is they've gone and looked at the amount of land, not just what's left above, but also what's bowing down into the mantle below. That's part of the effect that we see of these islands. So down here on the bottom, we have the age of volcanism. So essentially, Hawaii Island is over here on the left edge, and then Detroit Seamount's over here at the right edge. So from farther ago in time, we were having a fairly low volume of magma eruption, right? Kind of the best we can tell, with some possible up and down periodicity, right? Maybe because the mantle plume is getting dragged along and snapping back and dragging along and snapping back. That's one possible hypothesis of why it might do that kind of thing. But the longer term trend is clearly that in the last 30 million years or so, it started to rise at kind of an exponential rate. And so it's hard to really compare the values right here at this very, very left end with the ones farther over, because we have active volcanoes and we're out of equilibrium with this whole situation over here. But there's still high values in here. You can kind of see that the trend is still real, that really, especially in the last 5 million years, it's really skyrocketed, right? But in the last 30, it's gone up steadily for a while. So how come the hotspot's been putting out more value as well? I mean, that's interesting to think about as well. And we don't have all the answers, but we'll give you guys all the clues of how to think about this. That's all right if you guys don't follow everything, kind of just take what you like and what you will from this presentation. So you can kind of see that here is our Hawaii Island in the southeast, and we look to the next island over, Maui. It doesn't look that big, right? But you actually can look that if we rewind time back to 1.2 million years ago, that there is a much bigger landmass that's been termed Maui Nui, Great Maui, that actually connects this whole landmass of Maui and Molokai and Lanai and Kaho'olawe, all of that. That's all Maui Nui. And in fact, even this little branch out to here, right? And so that was the shape of Maui Nui. So that is a pretty big island as well, not that different in shape and size from what we have here. Maybe rotate it a little bit, but right, and here you can a little easier, more easily see Mahukona volcano undersea, northwest of Hawaii Island right there. So the islands are sinking, but you have to really account for not just what you see above the water with this effect. Okay, so if we look at what's called the geoid anomaly, that's essentially a measure of gravity. And what you can see is that we have this kind of background for the ocean, this kind of light green, blue, yellowish stuff. And then we have the gravity high, where the islands actually are. That makes sense because there's more mass here with there being land instead of water. And so you expect to have gravity high right along the island chain. But what you also see is this blue is a gravity low. And that's a trough that occurs and surrounds this, what's called the Hawaiian swell. There's a big trough, and it's similar to like lying on a water mattress, where you kind of sink into it, and you have a little trough around yourself. And so the Hawaiian Islands are lying on this mattress of the mantle of the Earth, and it's kind of pushing down with all that weight, and so it creates this big depression all the way around. And that's why it's so tricky to measure those eruption rates. Right, here's a little bit more zoomed in view on the top right, kind of showing that, you know, it's kind of a little more pixely, but a little more contrast here of how much the gravity is different there. And so I won't go into geoid any more than that. Won't get lost there. But there is, because there's a lot of other concepts to talk about. So we talked about that plume possibly dragging as a hotspot moves. As a hotspot is dragged by the moving plate above it, right? And so by one study by Lee et al. In 2004, this lithosphere, asthenosphere being in this more fluid part below it, that boundary underneath the Hawaiian Islands seems to have been eroded. So it's actually shallower over under Kauai than it is over here under the Big Island. And so the idea is that this plume is actually wearing, somehow altering or pushing up, some combined effect of it wearing away at and pushing up this whole crust over here as it's doing that, right? And then kind of on the outside is where you have that trough of it, where it kind of accumulates. So a lot of stuff going on in there. This has been termed the lithospheric washboard, for those of you guys are more geology nerds that like something to throw around. The lithospheric washboard is one of those. All right, so now we're going to turn to trying to figure out what the hotspot actually is beyond just the surface. Look a little deeper into the Earth. But to do that, we have to look at earthquakes, and we're going to really briefly touch on this travel time graph idea of how we've actually discovered some of the interior of the Earth. You know, some of this is really the whole Earth story rather than just the Hawaii story. So I kind of have to step back, and we're going to get a little bit more big picture here for you guys. But the idea basically is that if there's an earthquake at some place on Earth, then you'll have those waves will travel through the Earth and arrive at different distances away from that original location at delayed times. So it takes less time for it to go here than it takes for it to go there. So you can kind of map time on one axis and distance on the other axis, right? And kind of see there actually are on this plot 3 kinds of waves: P waves, S waves, and surface waves. Right? If you can imagine a slinky, a P wave is like if you're holding a slinky on the end of it and you're sending the shock wave through like in the same direction as it's coiled. Right? The S wave, it's back and forth. You know, the surface wave would be some kind of rolling up and down motion kind of thing. Right? That goes along the surface. The surface waves going along the surface. Right? And P and S waves both going through the media right through here. But because they vibrate in different directions, that means they travel at different speeds. So let me play this animation here of a simulated earthquake. This is another IRS animation. You can kind of see the P wave traveling faster arrives first, and the S wave arrives second. So you actually have this line of P waves, and a more delayed with a growing gap line of S waves, and a more delayed growing gap of surface waves. right? That's kind of the easier first step of it, right? That's kind of what we're working with here. And what happens when you have a boundary is that you have Snell's law comes into play. You have, here is a little slit of light, and it's shining on this boundary right here. You have part of the light's getting refracted. It's coming out at an angle. That's what refraction means. And it's getting reflected as well, right? So light is a wave, just like seismic waves, and seismic waves show the same property, actually, right? And so it turns out that when you have core layers, an outer core and an inner core, you have those first waves actually bounce off, or they'll refract through, then come out the other side and refract again, or they'll go through, refract in, bounce off, refract out, refract again, or they'll go through, go through, go through, go through, go through, all the way out the other side. You can have all these different paths, and all these different paths are kind of termed with different terminology, right? So instead of just a P wave, when it goes into this outer core region, it becomes a PK wave. Then if it hits the core again, it becomes a PKI. If it hits the mantle again, that's a PKIK. If it hits the mantle again, it's a PKIKP. Or reflection, it's a PCS, or it's a SCS. And so without going through all those details, there's all these different predicted dispersions of any earthquake wave. And so here's a plot from 6.7 Northridge earthquake, and all the distances all the way to not quite 180 degrees across the Earth, but close to 160 degrees or so across the Earth. You can see that exact P wave, but you also see the PP wave, and you see the PKP wave, and you can see all these other waves that are embedded in here. And so that's how we've learned what the structure of the Earth actually is from how long it takes a wave to get down there, and whether it bounces off or not, and how deep it bounces off. That's where all this information, because we can't see the core, we can't see these different layers, right? But we know how the earthquake waves behave moving through it. Now, interestingly, the S waves can't go through liquid. You can't shear a liquid. So S waves disappear in the outer core, and that's how come we believe it's liquid. And then they reappear in the inner core, because the P waves get refracted and they create some S waves also. It's kind of how it works. And so that gives us the kind of the view we need, but it takes kind of analyzing this kind of information. That's kind of the main study of seismology and structure of the Earth. Okay, so I kind of had to cover that first, because that's kind of the background for what this story is all about, because the story of Hawaii is a story of this whole structure of the Earth. And that's here essentially is that boundary, about 2,900 kilometers down, 2,800 sometimes. That actually varies, right? We've come to find out, because it's not as simple as this most common USGS image right here. I'll show you guys some little bit more evolved publications that address what they might look like in more detail. But so what we can do is we can then look at the differences in what we expect. I wonder if I can push that back. Yeah, so we can actually say, okay, so if my earthquake wave didn't arrive at this exact time, but it was a little bit slower or a little bit faster, then let's map out those differences. And if we do that, that's what these maps are. And that whole process is called mantle tomography. And so what you see here is a bunch of slices from the outer core boundary of the Earth to the surface of the Earth. And they've got depth here on the right. This is showing 410 kilometers, 660, and 1,000. And what you see here on the bottom, you can kind of see the axis of blue to red is 1.5 slow to 1.5 fast. So 1.5% faster is the stuff colored in blue, and 1.5% slower is the stuff colored in red. And if you start looking at these images, and these in particular are taken over different parts. This is Marianas Trench. This is the North Kuril Islands. This is West Java. This is East Java. Tonga, Chile, Peru. Kermadec Islands, right? All different parts of the Pacific, right? You can kind of see what might be a familiar pattern if you've studied geology, which is it looks like an ocean plate actually getting bent down into the crust there. So if you have ever seen this kind of diagram before, where we have our different basic plate boundaries, we have our divergent boundary where the ocean's kind of spreading to the sides there and there, and we have our subducting plate where the oceanic crust is going underneath a continent, for example. And you can kind of see it intact off of the image. Well, there's a reason I never drew what was below the image. We've been arguing about that for some time. But we're actually seeing what amounts to like a CAT scan or like an ultrasound view of the inside of the Earth showing us these plates. So here's a kind of schematic. We actually can see not only these subducting plate material, which in some cases we'll see there's evidence for them actually connecting all the way down to, this is the core of the Earth here, right? So actually coming up against the core, and in other areas which are much faster, which look like these mantle plumes, hotspots, if you will, right? Big upwellings that kind of surround different parts of the core. Now the core is not that big, so you kind of have this whole map. This is kind of the whole map of it right here. You have two spots that are kind of big upwellings, and then kind of in between you have two spots that are big downwellings, and that's kind of the structure of the core. At present, it has that kind of, areas where stuff is piled in more and stuff where it's coming up more, just how the cycle actually goes. We've been able to map out through this kind of study that there's ocean plates that go down and kind of flatten out, and sometimes they break apart, and sometimes they just kind of penetrate and seem like they sink down further in, and it's all kinds of crazy things you start seeing that you maybe didn't expect. So here's an example from Tonga. This is actually very close to, this is the area where that 7.7 earthquake occurred. So I'll show a blow of that in a second here, but in this area over here, we actually have various versions of the plate. You actually have areas where you might see two plates stacked one on the other, depending on which cross-section line, which slice you go through, right? So we actually can analyze these things in 3D, and it's kind of hard to visualize them in 3D. And so these authors have used origami to kind of illustrate what this actually looks like, taking a paper and folding it to show how you can have a slab going down actually with a tear in it, and one part torqued one way, overriding another part that's trapped below it, and they're actually the same plate. And this is a situation in Tonga Kermadec, right in there. So this is kind of zoomed into one portion of it, right in here, Kermadec Arc. And so I believe that earthquake today, 7.7 epicenter, was somewhere right in there, and I want to say it was only 10 kilometers deep. Right, so we're looking at our scale here. 10 kilometers puts it kind of right in here. And if you kind of look at this plot, these little white dots are all big earthquakes. And so there's a region of big earthquakes that's common kind of above this whole zone, right? Not only because the plate's going under, but because you have a big squeeze happening right here. And all that motion accumulates into the plate. And that's essentially why you have these shallower adjustment earthquakes. But you also have these kind of deepening earthquakes that go down to this 660 kilometers down. So when you saw like deep earthquakes in the last couple of years, even some big ones, they don't happen everywhere, but there are patterns of them happening in specific places, especially where you have these downwellings of these old ocean crust, right? Still on a surface over here, but actually attached and bent downwards, and then doubling up, piling up, being torn and bent. And that's the complexities of plate tectonics. So this is not quite Hawaii, but it's going to affect, this is all the stuff that's surrounding us here. We can do the same thing for Hawaii. So this is 6 different views of what is the Hawaiian plume. So this is the core of the Earth here once again, and this kind of reddish area is the connection of heat, where the big island is top and center of every single one of these cuts. And so in some cuts it's not quite so connected, in other cuts it's a little bit better connected. Sometimes it looks like it kind of meanders, like maybe it's not connected, what's going on, maybe it's drifting or blowing. And so, of course, since we have all these different ways to slice it, we can actually build these 3D renderings of it. So here we have 6 different cut depths from way down, 2,500 kilometers down, the base of this plume, kind of coming up, kind of behind my shoulder right here. And we kind of Hawaii is actually on here, drawn on here. right there. And here it is, 1500, there's Hawaii. So you can kind of see a little bit of this little plume coming up right there, 1,000-kilometer depth. And 660, it's a little bit more visible under Hawaii, easier to see. When you get to 440, it gets a little more muddled because you have a lot more shallow stuff going on over there, right? So, but that's kind of one way to kind of slice through it. And so you can slice through. This is a view from south to north with Hawaii at center. And you can kind of see here's that big zone of red that actually feeds other parts of the Pacific. And we kind of come off separate to Hawaii from off of that. So there is our Hawaiian plume imaged by earthquakes. It looks like that. And not only that, they've done models with flow, like how the material is actually flowing within these areas, right? So you can kind of see it. Maybe you guys can't see so easily. Those little arrows showing the flow directions within here. So we're going to focus in on the actual Hawaiian plume. So if we can kind of just look at that phase right here, Hawaii is right here, top and center, and that is our 3D Hawaiian plume, right? Kind of at the edge of this other big blob that exists to our south and west over here. Not quite sure which color to use. There. And a little bit less connected in these couple of slices right in here, right? But there's probably some other view that connects these things together. And there it is. That's the Hawaiian hotspot, French and Romanowitz. Now there's a caveat. Caveat is that this has been tried several times, right? And sometimes what you find is that you don't have the resolution. This is bottom. Look at this bottom image first. It's kind of showing if you're on a surface and you have all your seismic stations spaced at 5 kilometers, and your aperture is 160 kilometers right here, then resolution, kind of like a camera, where can you get the best focus? It's an area, it's a triangle kind of that goes underneath here. You can see pretty well in this square, but once you're outside of that, you're in a poor range, poor resolution. So depending on how you do this, some people will call it a little bit of magic. Sometimes you don't produce a plume image, right? So kind of a caveat, maybe there is one, maybe there isn't. What's going on up here? Maybe this is accurate, maybe this is that kind of shallow dragging part, and this is that deeper part, but it's really hard to see what's going on. And that's because of this resolution issue, which is always an issue. And this is why we leave it to the experts to publish all this kind of really intense research.
We do have a super chat that just came through from Gary Bryan. It says, very complex, many unknowns. Thank you. We also had one
Gary.
on Hawaii Tracker from Brian B. Thank you, guys. Appreciate it.
Mahalo, mahalo. So here's
also, I am collecting questions to get into the chat, and we will be doing those at the end.
Yeah, for sure. I'm sure there'll be all kinds of questions, and I have to jump back in here.
Oh, you have no idea.
I'm sure that every thing I put up generates probably 10 questions. So here, for example, is a little bit of that caveat in play. 2 different views of the Iceland plume. And on the left, we have a publication by, not sure how to say these gentlemen's names, or these people's names, Beward and Spackman, 99, and also Ritsema 99, with a similar kind of study, found no deep hotspot for Iceland, whereas a deep spot was imaged by Beward and Spackman. So depending on how you tune it, how you focus it, how you turn the dials, and how you analyze the data, there's a little bit of art and subjectivity here too. So, this is why this is a very complicated field. And one of the big issues is trying to deploy more seismometers to really see what's going on. So what do we see elsewhere? Here's another one. This is Yellowstone. So here is USGS image, actually publishing University of Texas research. And here from very deep down, 2,500 kilometers at least, 2,800 kilometers is the boundary, we see a mantle plume coming up to the shallow area, right? Right under where Yellowstone is. So same thing, same caveats, but once you can someone can focus in on it, then it kind of leads to more research and more interest in an area. What's going on over here? So That's the whole basin and range, probably, yeah. Extension of the whole southwest area of this North American continent. That's a story for another day. That's why there's young volcanoes, you know, that are active volcanoes less than 10,000 years old in Arizona and in Mexico. It's this kind of thing. So, all right. Here's kind of a lengthwise view under North America. Great Lakes kind of over here. And you kind of see some interesting things. We actually have these slower areas in blue. That's our continent, right? With, you actually see where the glaciers were. The mantle is flowing back up. It's like someone got up off the waterbed, and it's springing back into shape. Right? The glaciers melt pretty quickly, and then the mantle adjusts slowly, so the mantle is kind of filling back in, and that's why you get earthquakes in Michigan, in New York, in areas like that. It's because of that kind of process and that kind of adjustment. Right? And there's kind of that whole spreading in American West kind of area, right? But if we look at just the blue thing now, we can notice there's actually two more things over here, right? There's actually two older submerged slabs that seem to be, in this case, or seem kind of stuck there. There's a gap between them and the core, but there is a little blue blob under here, under North America as well, right? So what's going on there? Like, you know, so obviously you can see that there's some history of the Earth preserved. This is what's been termed by one of my old advisors as a fossil slab. And here's a study of his, looking at 200 million years ago, over underneath Siberia, closing of the Mongol Okhotsk Ocean. I probably butchered that name as well. But you similarly see two big blobs of slower material, right? And the idea being that if material is colder, then the seismic energy can travel through it faster, and that's why it's that 1% faster. And if it's hotter, then it goes through it slower, and that's why it's that 1.5% slower. And so you see those slow areas, but you also see hot areas. So former ocean that's all the way closed, and now there's a continent sitting over where there used to be an ocean that closed over here, all of North Asia. And then you have the active Pacific plate subducting right here, and you have a big blob of it seemingly deformed, but actually connecting all the way down against the core of the Earth, and what he's termed a fossil slab graveyard. Right, so these are the fossil slabs, and the ones that can actually penetrate all the way down and collect against the core are the ones populating this graveyard, these fossil slabs. Now, this is obviously a real conundrum, right? You're going to get some of this really cold surface material, these old crusts of the Earth, and you're going to pile it through the whole mantle, not remelt it, but keep it coherent until it actually piles against the core of the Earth. Now, it can't end like that. And so one obvious solution is that you have heat flow from the core into these cool areas, right, to kind of equilibrate. And after some time, once it actually equalizes, the heat flow doesn't just shut off instantly. It kind of keeps flowing in there, and essentially you have areas that go from being heat sinks to being net heat positive, right? So that from that point, they want to become buoyant and rise up. So, but let's look at that boundary first. And so here's a image from Jean Lowe's and Thornley in 2005, and structure of the Earth. And now they're actually putting in a little more detail of what's happening in here, and these kind of lower limits here, kind of the first little hint at this, what they call the D double prime layer, a very special seismic layer. And this is why, if we look at this image here on the left, I'll read it to you guys. On this left side here is depth in kilometers. So all the way down to here, it's 6,000. So this is the center of the Earth over here, right? The core boundary is right there. So all this is the mantle. The crust would be just right up here, like a really thin little thing. So when you kind of see all the lines having this variation, that's all within the crust of the Earth at the very, very, very top. So when you get to, let's look at the first thing, this blue line is density. The density at the surface, you can see climbs with depth, more slowly through the mantle. Once it hits the core, it jumps up, right, by over a factor of 2. So the density of the core is an order of 2 greater than the density of the stuff in the mantle, right? So when we're looking at that stuff trying to penetrate, these slabs trying to penetrate into the core, they can't do it, right? It's 2 times denser. It's like trying to walk through a wall. It just can't happen, right? So that's And then within the core, you see an increase, another jump.
I can't make...
Increase, another jump. And into the center there. I got a bug on my computer that seems to do that, so sorry guys. All right, so that's the most important thing here is the density and how you can't really penetrate through there. If we look at the actual wave velocity over here, density is plotted down here on the bottom actually. Wave velocity is up here on the top, and that's what this shear wave velocity is over here, kind of increasing through the mantle, disappearing in the outer core, reappearing in the inner core. You have your P waves that also increase with depth, right? There's some complexity in here, which is kind of the whole crust mantle boundary and the moho and all of that, which is not relevant today as much. But they increase all the way down as well. So you can kind of see that this is the place where all these things change. It's a D-double prime layer, and that's why it's a layer of interest to seismologists and researchers. So if we look at just the thermal effect of the core, it might not be quite enough. Some models kind of just show, instead of showing a whole plume that kind of comes up, it might start trying to come up, but then you just end up having these hot fingers that dissipate. So it may be that temperature by itself is not quite enough. And what's turned out is that there's been quite a lot of research done now using diamond anvils. And so in this kind of summary, this is kind of what it looks like. You take two diamonds and you put your material that you want to study in the middle of here. And in this case, what they were trying to study is two materials. They're studying iron as a representative of the core of the Earth. And they're putting in what they think is a mantle material, something that's technically a magnesium perovskite, but it's kind of a cousin of olivine. Think of it that way, right? It's kind of, you know, that kind of similar kind of thing rearranged. And so they put it in there. They can squeeze it to the pressures found at the depths that these reactions are occurring. They can also, because this is diamond, they can shoot a laser through the diamond and heat up the sample to whatever temperature they need until it's like glowing hot, whatever temperature, and then they can actually then simulate the temperature of the core mantle boundary. And it's really been the advent of this kind of technology that's allowed us to study the kind of reactions that happen. And they can kind of see like, okay, if you put iron against that magnesium perovskite, you actually start reacting them. They react instantly, and there's a clear effect, and so that's something that happens. And so without going into the detail of the chemistry of it, I'm going to show you guys some of the detail of this now, that you have a reaction zone, right, where you have this kind of downward convection of mantle material and possibly some of those fossil slabs. And as soon as they touch any of this liquid iron, right, liquid iron alloy in here with whatever other impurities it's got, sulfur and nickel and whatever else is in there, as soon as that happens, it starts reacting. And that reaction produces these dregs, which are kind of piling up over here, and quite possibly also influencing this upper part of the outer core of the Earth that's actually spinning at this meters per second rate. So it's not only a temperature effect, but it's also a chemical effect, right? You're having a chemical reaction happening. And that chemical reaction is producing this material, right, that's creating a topography on this core mantle boundary. Okay, so we have a new paradigm for this whole situation, right? So here in the center we have Hawaii, and so we have that kind of cores down there. We have that ultra low velocity zone. We have this area of melt inclusions. We have that D-double prime layer, and we have through all that our mantle plume coming up. And there's other areas where you see that structure is actually much higher, and next to it you see these strands of other hotspot plumes that kind of come off the side. And it turns out if we zoom into Hawaii, we actually do have one of these over here next to us as well, kind of over here. That's not really drawn in this particular view, right? But you can also have these other zones that may park deeper within the Earth and become inactive hotspots between South America and Africa, for example, or be still connected and erupting like Galapagos, for example, areas like that. But this is all driven at the surface which is why I started talking about this, by what's happening down 1,800 miles down, 2,800 kilometers down below us at this core mantle boundary. So when we start imagining, okay, so it's coming from the core mantle boundary, how is it actually getting here? How does, if the material is actually rising, what does it do? And it turns out that this material, as it rises, starts off, kind of you can't really see. I'm going to draw it right here. The first little rising diap here looks about like this shape and size, and it's all solid because the material rising up essentially is encountering friction on the outside, right? So you kind of have friction on the outside of this rising amount of material, and so the very top of this can't rise as quickly as material can move through the middle of this conduit. So you kind of end up feeding the head of this plume faster than the plume itself is rising. The plume starts wrapping back on itself on the sides, more and more and more. This one's wrapped all the way over like that, right? Until eventually, imagine by the time it gets to the surface, it's totally wrapped up, and you have a much broader area of hot material that wants to erupt than the actual plume started off being. But once you might get past that first phase of massive eruption, geologically survive it, because it's a millions and millions of years process, then you might have this established plume that can kind of come up and feed from below to the crust. So this is kind of how we imagine that the plumes rise up from the core mantle boundary towards the surface of the Earth. And here is a Graphics Arts image showing that. This has been used by USGS. Core mantle boundary. There you have that material, rising plume that has a head. Once it hits the surface of the Earth, then it creates large areas of eruptions at the same time, which are termed flood basalts. Right? If you guys have heard flood basalts, often related to this hotspot initiation, and also sometimes called large igneous provinces, lips. And after that initial plateau is carried away from the hotspot, then you have your trail kind of following behind it. So that's kind of the overall model. If we look at hotspots worldwide, there's some clear examples, like Galapagos is an easy one. Over here, where the hotspot currently sits, there's a trail that leads back to, it turns out, most of the Caribbean plate is the big burst out of the Galapagos. Right? Iceland is kind of all sitting in one place. It's harder to tell what's going on there. But places like Samoa and Easter Island over here, Tristan da Cunha, Afar, Réunion, that goes to the Deccan Traps in India, a famous one. Kerguelen's kind of got a big blob over here. That's kind of a little bit more complicated. I'll have to go into that in a little more detail. But it turns out that quite a lot of these hotspots do have large igneous provinces attached to them. Sometimes easier than others, right? Here's Yellowstone over here. Over here, kind of point out for our North American viewers. And so all over the place, right? So Hawaii is over here. It has a trail, and it's cut off. So we don't get to see, actually, on the surface today, very easily attached to where it used to be, what started off Hawaii. But it's a natural question, so we will explore that. And the way to do that is kind of look at the reconstruction of the plates, and I'll get to how this is done here shortly. But it turns out that 140 million years ago, the Pacific Plate was born out of the middle of three other plates. One called the Izanagi, one called the Farallon, and one called the Phoenix. And out of the middle of those three plates came a little triangle of the Pacific Ocean that grew. And we know this from the magnetic anomalies, which I'll cover also shortly, that have this triangular shape. So we'll point out this triangular shape later on. And it kind of grows. We can kind of track the different magnetism of the seafloor over time and kind of see how the Pacific Plate grows and moves in this direction and consumes the whole Izanagi Plate to the northwest. The Kula Plate still what remains of the Farallon over here. Kula to the north, the Farallon over here, and the Phoenix is completely gone here to the south. So the question is then, where was the Hawaiian hotspot during all of this? Because that's what's going to matter. It's like, depending on, this is a canvas, the background of what's happening, and Hawaiian hotspot might pop up somewhere. And then which plate, is it on this plate? Is it on this plate? Is it on this plate? Which way would it go? Is it on the edge? So that's what we'd like to examine next. But to do that, we have to go back to another kind of novel approach of studying the Earth, and that's looking at the magnetic field generated by the core, so it kind of relates to what we're talking about here. But kind of briefly, we have our magnetic field, right? The Earth is like a big magnet with field lines that kind of go from south to north, right? Just like if you put down a bar magnet and compasses next to it, you can kind of see that metal shavings will align in the shape of that magnetic field, very similar to the Earth. So that's just how it naturally is. There's a difference between a magnetic pole and a geographic North Pole. And that may be a story for a different day, not to get lost there as well, right? But so one thing you can measure on this, besides the intensity, is you can also measure on the compass what's called declination. So on my compass view over here on the left, this is the direction, like on the surface of the Earth, right? Which way is it relative to magnetic north? But also there's something called an inclination, which is how much does it dip down from horizontal? What angle is that? Because you might notice that at the poles, that angle is near vertical, and by the equator, that angle is near horizontal. So it turns out that if you can have metal around, and I've mentioned that our lavas are already very iron rich, and you can actually cool that iron in a certain magnetic field and preserve it over time, you can then tell a lot about the history of the magnetism of an area, or a big area, possibly the whole Earth. So this is kind of the basis for that, how the magnetic field works. And the magnetic field is, of course, what provides us the magnetosphere, this kind of protection from these ions that come flying over from the sun at us. And so it's a very important thing to study, how the magnetism of the Earth actually changes, and it's related to all this process of Hawaiian hotspots as well, because that's part of the reason for understanding this core mantle dynamic and what's changing inside of the core. So kind of see in here the spinning core. It's thought to be spinning in the order of meters per second to generate the dynamo that we see, the magnetism on the surface. So in actual practical terms, they believe that because it's all, the whole Earth is revolving, there's a spin that kind of goes around. Oh, I need a different color. So there's a spin that kind of goes around this way, and then within that you have these other coiling spins that kind of surround the inner core, and it's through those that we essentially are creating field lines, right? This is all liquid flowing hot iron under pressure, and it's flowing at these meter per second rates, and that's what's generating a magnetic field that's permeating the entire planet. All right. So it turns out that from eruptions in places like Oahu and other young volcanics, you can actually go on the cliffs of what are lava flows, and lava flows have lots of little iron crystals, and a lot of them are like little compasses. You can then go and then first of all, you're saying which way is north? Is north towards our current north? And they've drawn that on here as a black bar. And if north, according to the rock, is towards our current south pole, then they've drawn that as a white. And they call these normal and reverse periods. And so here is the whole geomagnetic time scale of the Earth. And this is actually used because you can, it's almost like a fingerprint. If you find a little section that got exactly that pattern, it has got to be right there, and it can't possibly be anywhere else on a scale because of that unique pattern kind of fingerprint over time. Right? So 0 is over here, 5 million years, 10 million years ago, 50 million years ago, 20 million years ago, 25, this is 40, this is 80, 120, 165 million years ago. That's how far back we have this magnetic time scale. Beyond that, it gets a little troublesome. We'll get to that shortly. There's not a whole lot of rock left that's easy to make a continuous scale from that point forward. Whereas if you have a hotspot erupting for at least 80 million years, then you have a pretty good record of especially this younger stuff right in there, right? And so some of the cliffs of Oahu and Kauai you can actually go and you can say, well, part of the cliff is normal, and this part is a reverse, and this part is normal, and this part is reverse. Right, and that's kind of how we come by doing this, and actually then relating it to an actual time. So what you can see is it's flipped a lot. There are times where it's flipped a lot in a short time, and other times where, especially through here, the long Cretaceous quiet zone, it stayed steady for a long, long time. So that can happen too. But we're in a period now where it's been more flippy, with some longer periods, kind of similar to what we see in the last 20 million years or so. So the details of that perhaps for another time. But what actually happens then is that as lava comes out of the ocean ridges to form the seafloors, the actual poles of the Earth will flip, and then the iron will point north on one line, and then north in the other direction on the next line. And so we actually have this map of stripes of the seafloor. It's essentially a map of polarity of rocks on the seafloor that ends up being something like this. So that was a fantastic discovery for the proponents of plate tectonics, because that would really allow them to show a lot of this effect in incremental fashion rather than an abstract fashion. And it's very useful now beyond that, because we have now this whole map of the Earth, ages of the ocean floor for magnetic anomalies. And what you might find is that the darkest color on here is this dark blue, and that is about 180 million years ago. And it turns out the oldest ocean floor is that age. And that's because universally, when it comes time for an ocean plate to collide against either another ocean plate or a continental plate, then the thing that goes under is always the older ocean plate. So you end up recycling the ocean crust, but you don't recycle the continental crust. That's like the scum on the Earth. Instead, the continents kind of float around. They never really sink in. Whereas sometimes edges of islands will get scraped on continents, and so continents can have things stuck onto them, but they kind of move around on their own, bobbing on the surface as well. And really, what's the more active part of the Earth, surface of the Earth is all underwater, right? And Hawaii being a little exception right over here, but you can kind of see that the reds are the youngest stuff here, and that's where the active seafloor is spreading. The youngest, this is that giant underwater mountain range. That's the spreading ridge of the Earth. It kind of goes all the way around, loops around, and there's the one that goes all the way around Antarctica as well. You kind of follow it all the way around. So a very interesting thing there. And so here is our Hawaiian hotspot, Emperor Archipelago trail on that feature right there. So, and that's where we get the boundaries from the plates. So when we come to tectonic plates, this kind of all comes from the same place. It's the boundaries that we see. There is that same spreading zone right in there, and you can kind of see areas where continents are separated from oceans, but that's where the boundaries for continental plates come from, is from that kind of mapping, most of it being underwater, and other parts, of course, being on land, but overall, most of it's underwater. So here's an animation from Scotese.com, and this is a reconstruction, right? So if you actually you can rewind by, let's take away the very minimalist layer, and let's put it back, and let's put it back, and let's put it back, and that's how we actually have reconstructed Pangea. This is an animation from Chris Scotese. I'll play it one more time. This is kind of undoing it, rewinding, and it's showing the Atlantic Ocean essentially closing, and now it's going to normally open. This is how it actually went, by undoing all those magnetic stripes. And it's kind of see, here we are. Hawaii's here, so we're kind of coming around, spinning from the left, the back end of this thing. Right, so not as clear to the center part of this animation, but kind of shows you how this game is played and how we can reconstruct where different plates were at different points in time is from this kind of process, right? So here is Pangea without the plate boundaries, showing just the continents, and it's exactly that same pattern. So I'll pull it back and forward again. Same thing. Another Chris Scotese animation, who's fantastic. He's been doing this ever since the time when he had to do it on paper and do flip books for us to see animations before there was a YouTube. All right, so that was Pangea. And one more kind of showing in a map view this how we got from Pangea to the whole Earth by kind of opening up sequentially all the ocean plates. So that's it. That's how it works. And so if we look a little more closely at Hawaii, what I've done now is I've taken this color scheme and I've superimposed it for the same ages on the Hawaiian-Emperor chain. So you can kind of see that even though we are on this kind of greenish material over here, which is in the 50 million year range, 60 million year range, we're actually burning through it most of the way, right? A little bit slower over here at this far north end. But we see a stark contrast in color for what's actually coming out to what's actually there. And the bend relates around 47 million years ago. And we're still going to come to that, I promise. And if we look in more detail at that bend, it's 47.5 million years falls right in here. You might notice it's not exactly straight up right there. There's a little bit of there's an in-between segment. It's a little bit of an arc. It's really a range of 50 million years to 47 million years when you zoom in real close of when this bend actually happened, right? And you kind of see the ages here. 52 on Koko, and here 38, greater than 38, greater than 41 over here at Abbott and Kalahan. All right, so we know where all these seamounts are, and what we can do is we can then pull the rocks from these places, and we can then try to measure what the inclination of the iron crystals in that rock happens to be. And from that inclination, there's a mathematical relationship. You can say, okay, that means it was at this degree of latitude when it erupted. And so if we do that for our rocks right now, come up 20 degrees north is where we are here in Hawaii. So that's where it is. If you go back to Abbott, in fact, everything between Yuriako, Midway, Nihoa, all the way to Hawaii, everything shows up as a 20-degree north signature right in there. If you go further back on this Emperor part of the sea chain, you actually see it starts off in that same range, 23 plus or minus 2, 26 plus or minus 9, 27 plus or minus 3. Detroit's up here at 34 plus or minus 5. All right, now there can be some little variation. There's some error in here, of course, but big difference between 20 degrees north and a rock that's saying it was erupted at 34 degrees north latitude. And so that means the hotspot had to have been further north when this erupted, and then a little bit less further north, and then a little bit less further north, and then a little bit less. And then since about here, it seems like it stayed at the same latitude for some reason. Right? And that latitude is the one that we are currently at right here. This is not the only way to look at this. We actually have, it's probably too small for anyone to see here, but we have ways to look at fossils, right? You can look at sediment, like the sediments that are raining out on the deep ocean floor, and all little critters that are microscopic that live in the ocean column evolve over time. And so there are different ones that occur at different geologic eras. You know, there are different ones that were alive 80 million years ago than are alive now, and some of the same. But the actual assemblage of them all together is also unique to time, right? So you can actually say, okay, well, if we go back, not only that, you actually can go and get the latitude of those kind of sediments, right? So what they actually find is that latitude also increases back to, they find, it's hard for you guys to see over here, but in a range of 30 to 35 degrees northward drift as well, possibly, right? As at the high end of this, and at the low end of it, somewhere around 20 degrees of drift. So the sediments are also showing, well, it's really hard, I'll grant you, to both measure magnetism and sediment of an 80 million year old rock that's been submerged under the ocean for that entire time, with all kinds of stuff happening over top of it. So all with a grain of salt, but that's kind of where the thinking began, right? And what's most recent, 2017, Torsvik et al. Have done reconstructions trying to see if you could just move the hotspot down, and that's kind of now shown in this little inset down in here. This is a motion of the hotspot, moving from this is the best fit. I'm just showing you guys the actual result without going through all the steps, but the best location of where it started off and migrated to the south, a little wiggle, right? And through that time, the Pacific Plate was moving to the northwest. As you might think, oh, if the hotspot was moving during this time, but not moving as much during this time, then maybe this bend is just because of the hotspot. And what they're finding is that, actually, no, the hotspot does need to move to the south for sure, as much as 10 degrees of the Earth, right? That's 1,000 kilometers, like 600 miles. The thing could have moved to the south, right? That's a long way for it to go. It's definitely not stationary at that point, but it's also not enough to account for the full bend of the seamount arc, right? So they've shown in red here what the track would look like if the hotspot. I'm sorry, if the plate had not moved. There's just the hotspot motion, and over here is a combined motion, and you kind of see these big error bars, kind of these farther ones over here. But you kind of see that we're hitting 80 where it's supposed to be 80, and 70 where it's supposed to be 70, and 60 where it's supposed to be 60, etc. It's a best approximation. So we actually had to have a change in a movement of the plate direction, and the hotspot moving from some location to the south. I can go into a lot more detail about that, but I could easily get lost there. But part of that whole process as well is that you can look at slices through the Earth based on that whole tomography, the imaging of inside of the Earth, and we can kind of see at 700 kilometers depth on this top panel over here. This is today on the left, and 60 million years ago. The flow is fairly similar, south to north. So that's kind of 700 kilometers down. For the mantle, that's shallow. That's the shallower part of the mantle. Whereas this over here, 2450 is a lower mantle. So at the lower mantle, the current actually goes north to south. Not only today, but also maybe a little bit more northwest to southeast 60 million years ago. This is something we've actually, because of all this earthquake and imaging and modeling that's kind of gone along with it, been trying to recreate what's been happening to the Earth through its entire history based on the scans we're taking today and what we know of all the materials that comprise it. It's really fascinating stuff there. And so if you look at this, south at depth, that's the motion of our hotspot, and that makes sense that that could have been the case 60 million years ago, been moving in that direction. If you found it was moving against the current, you might think, oh, hold on a second, something's wrong, or how do we explain that? But since it does fit, that kind of lends this to be the favorite model. Instead of it coming from somewhere over here, farther east, and moving more west, right, which would kind of be against the current more so. So, very, very brief recap of this research that's, much more in depth than this. I'm just pulling a little bit from here and a little bit from there, just so you guys can see a little bit of how this works. But here's why a plate might change its direction, right? So I've showed you guys a little bit in one view. Here's a Pacific Plate in this earlier frame, 57 million years ago, the Paleocene, and its motion is in this view up, right? These blue arrows, right? Here's an Emperor chain forming, and the Kūlau Plate over here to the north, a Farallon Plate is over to the east, and the Izanagi Plate, the very last bits of it are over here in the northwest, right? Why? Because it's subducting underneath the edge of the continent over here, and this is the last bit of it left before it spreads under, and it's going to be completely consumed, and it's going to be all the way gone. When that kind of thing happens, like this, where this plate was the one that was moving in that direction, and suddenly it's gone, you might find that suddenly the Pacific Plate now is moving that direction as well, and the Kūlau Plate is also moving in that direction as well. Right? The Farallon Plate is also in various stages of consumption over here on the right side. But that's why you might have a plate change, is because you might have an old, you're essentially rearranging. You have one less plate, the plate's all the way gone. And we talked about, I showed you some of the things about how they can detach or break off, but that's why it can change direction. And so that's what's believed to have happened. And some other kind of evidence that was going on. There's a lot going on this image here, but look here at this first northwest part. Here's Hawaii, the Hawaiian island chain. There are other tracks of other stuff on the seafloor as well. And so one of these is called the Musicians. This is the musicians' seamounts over here. And kind of zoomed in this panel below right here. And see, these are the musicians' seamounts kind of running in a similar kind of direction over here. And they have ages. It's probably hard for you guys to see, but they're written in white over here. 83 million years, 75, 86, 91, 94, 96 million years for this one up here. This is all happening early on, possibly at the same time as the early Hawaiian hotspots active. We don't know how much beyond the 80-85 the Hawaiian hotspot actually went, because we don't see the beginning. We don't know how long it went beyond that. But so certainly by the bottom part of this one being active, the Hawaiian hotspot is also active. So you can kind of see there's multiple spots. But also what we're going to do is we're going to zoom into these little squares here and here, right? We're going to have these kind of ridges that are appearing more east-west, right? Kind of near this big Murray fracture zone, which is kind of related to the spreading of the crust, and so kind of natural weaknesses exist in the crust. But if you zoom in there, some of these show ages of 92 million years, 94 million years, so kind of similar, there was some torque, that some crack opened up, and it wasn't as simple as just one hotspot chain. But then down here in this lower section, in this area called Bach Ridge, Beethoven Ridge, they're finding ages of about 50 million years, which is about the age of the changing of the Pacific Plate. 47, 48, 52, 53 are ages of all these different places. So it's almost like the whole Pacific Plate changed direction, torqued, opened up some gases, and those gases erupted for 6 million years and formed these long ridges out of the seafloor, not from hotspots. The kind of lava they find here is not the kind of lava we have here in Hawaii. It's lava that comes from this shallow mantle, as if it was just leaking up through a crack. A giant crack through the earth that lasts 6 million years to kind of plug up, right? So there's also evidence for the torque, and really you need both. You need both the plate changing direction, and you need the hotspot moving to kind of accommodate that effect. So if we go back, revisit this image here, and go back to, this is 140 million years, birth of the Hawaiian plate, or the Pacific Plate. Over here, the Hawaiian hotspot is somewhere in a range of 80 plus, maybe 100. So maybe this middle frame, we're at 100 million years, might be where we actually are. And we now know that we're maybe 10 degrees north of where we are, more or less now, right? That's kind of hard to see where this is on here. But it's somewhere around this zone right in here, which is just drawn on here, dotted. We don't know exactly where this was, but somewhere in the range of here, where we know there is enough heat to generate the triple junction between 3 plates spreading, right? That could be a situation, right? I'm not quite sure what this boundary over here is, right? Maybe this one isn't actually spreading, but this one is certainly spreading, and this one is certainly spreading. And so that's a zone of heat, and we have seen hotspots associated with other areas where the continents have spread apart, similar to between South America and Africa, right? And that's the whole idea of a thermal blanket, right? So when I showed you guys the picture of Pangea, Pangea is covering all of one part of the mantle of the Earth and none of the other. So under that area, the mantle is essentially blanketed, can build up heat over time, generate heat flow, pop up through the crust as hot spots, and then tear that supercontinent apart. So all supercontinents are doomed to break apart and travel around a globe, and then it's a globe, so they're going to re-encounter at some point, and then they come back together apart.
So how long until you get beachfront property in Ohio?
This is all geologic time. That's kind of, all like a big picture. I've zoomed way out in space and time through this whole presentation here. That's kind of where we need to go to kind of examine the origins of Hawaii. And, that's kind of something people have been asking about. And usually I don't go way out in a tangent, but that's the whole point today, is to go off on this tangent. So here we are. All right. So back to that. There's a few possible places, if you look at the west coast of North America, you can kind of see all these what are called suspect terrains, right? Terrain spelled Terrane, that are essentially some piece of land that got stuck onto the continent over here. Right, so this was actually originally published as the Great Terrain Wreck by Coney in 1980.
He probably patted himself on his back for that one.
Many of us appreciated some levity in the sciences at that point in time, right? But in any case, there's lots of different things stuck on here, some of which might be some of these old metamorphosed, altered, cooked, deformed pieces of the Hawaiian plume head. So it may just be that one of you guys out there watching may be so inspired to go out and study this someday, and maybe you guys can find out where it is. This is one possible piece of the Pacific Rim where it could have ended up. Right, it could have gone in any of those directions, right? But it could have ended up over here, and so maybe over here is a piece of original Hawaii that's been cooked, and it just takes the right person examining it the right way, with testing that kind of theory to find what might be going on over there. So it's still to be determined where exactly it went. So that brings us to the last kind of point here that we're going to discuss, which is kind of the most advanced part of all this. What you guys actually asked for is this whole a.k.a. volcanics discussion on Hawaii. But in order to discuss that, we have to kind of know all this other stuff first, which is why I've taken us through this journey. If any of you guys are still with me, having gone through all that, it's okay if you didn't get it all. But we come to the point now when we start looking at the volcanoes of the Hawaiian Islands, and we're looking right now, especially at the main Hawaiian Islands from Kauai and down. And we find that the chemistry of the rocks of the volcanoes is similar along one lineation that we call the Loa trend that lines up Ko'olau, West Molokai, Lanai, Hualalai, Mauna Loa, and Loihi. And then we have just slightly to the east, connecting Kilauea, Mauna Kea, Kohala, Haleakala, West Maui, East Molokai. And then kind of disappearing as far as we know, because we haven't looked past here to see where these go. So we only know this far, except that we know that the emperors are all Kea on this trend. So this one that seems like it kind of disappears right in here might have been the original one, and then at some point Loa has to come in from somewhere. Maybe it pushes Kea out of the way a little bit. Maybe they just haven't found the Kea over here yet. Maybe it's this part of collapsed Oahu over here, right? And that's still to be determined. That's kind of where the research is. And if you kind of look at over here on the top right, we've been set this kind of flux again over time, like how we've really had a big increase over the last 30 million years of magma coming out. Is that the Loa trend suddenly kicking in 30 million years ago? And if so, then that's where we need to go and look. And so there are researchers going and looking for exactly that. But of course, you got to go by boat and bring our equipment and dredging stuff. And it takes a very specific scientific cruise and vessel to do that kind of thing. So that's kind of the where these things actually are. What is the actual difference? So there's a lot of different ways to look at this. You can look at all different kinds of chemistry of it. I'm not going to do that to you guys. I'm not going to put you through all of that. I'm going to show you guys the most obvious one, which is this lead isotopes, right? And so without going into what this ratio actually means, I can show you guys that the volcanoes in the Loa trend are drawn up here, right? That's the line with an error bar, kind of error envelope, you might call it, like that. Right, a little bit higher ratio of 208 lead to 206 lead. And then the Kea trend, a little bit lower trend. Here's the actual islands. And their possible error envelope of the Kea trend. There's some overlap in some of these areas. There's probably some blurring, right? There's a lot, this work is not easy. But this is a very, recent way to look at it, right? The 2011 paper by Dominique Weiss, University of British Columbia. And here's an histogram form. You can kind of see of the whole population of all the values. The Loa fall with a clear peak over here, and the Kea fall with a clear peak over there. So there's a clear difference in the chemical signature. That's the easiest way to see it, is with lead. There's all kinds of other trace elements, but without going through the periodic table and having some really being into the chemistry of it, we'll kind of leave it at that. So here's a proposal. The proposal is that big fat blob of material that's building up against the core over to our southwest suddenly got tapped, and that is where the Loa material is coming from. So we're now entraining stuff from that big blob, but also the regular Mantle stuff as a a.k.a. trend. So we started off with just a regular hotspot moving through the Mantle, and it turns out that when you have the big topography on this inner planet that we have here, right, that has this kind of crust and, you know, mountains on it and valleys and all these features with, you know, very active stuff going on, which is influencing the whole surface above it, 2,000 miles up, right? That this thing found this boundary, and they believe that this is a great place to park your hotspot. That the dynamics right here are such that it kind of catches hotspots, if not generates them. So right in here, and we have coming through this 1,800 miles of the Mantle, side by side, the Loa magma and the a.k.a. magma, and it makes it up through the crust of the Earth, and they erupt, what, 60 miles apart for millions and millions of years across the seafloor, which is kind of an amazing thing to consider if that's the case, right? If that's how it actually is. And so people have been trying to validate this and go into more detail, and you know, how can this possibly be, right? So here's another view of that low velocity zone in the Pacific right in here. And this one is actually drawn on these yellow dash lines. Let me switch to yellow here. And these yellow dash lines where you really have the steep sides, where it's the most conducive to this hotspot generation, right? And so they actually can go through and map. Oh, we actually expect hotspots over here, and we expect hotspots over here, and we expect hotspots over here, and we expect hotspots over here. And they can kind of go through, and it doesn't match up exactly, but it does match up, right, to some degree. And so now we have not just temperature, but a chemical reaction. We have thermochemical piles. Right there they are. And then here, coming up to Hawaii, is our hotspot. And there, coming up, it's a hotspot. And there, coming up, it's a hotspot. Right? It's kind of like that. So, looking elsewhere around the world, you can kind of compare Tristan da Cunha is the one in the Atlantic. And we have Hawaii. We have Pitcairn in the South Pacific. We have Kerguelen over in the South Indian Ocean. Right, all at the edges of these red, low velocity zones. Right, so that's the new thinking of why here is, well, because this is where the edge of that lower blob of material, which is now the product of an old ocean crust that sank all the way to the liquid outer core of the Earth and reacted with it and now made a core mantle boundary mountain, right? That if I go back, is 1,000 kilometers high, right? That's a huge feature under there. And so here is the tomography view of all those different hotspots. Here's Samoa. Samoa, again, slightly different view, and Tahiti, and the Marquesas, and Galapagos, Pitcairn, Cape Verde, Canary Islands. Iceland, not showing quite that deep signal. We'll see. McDonald. Not quite a deep signal. Balleny. So can I see you have your different kind of shallow hotspots, deep hotspots here in this particular case. Yellowstone, not showing quite as well, but if you turn up the gain, you can kind of see there's a little bit of yellow right through there. That's that image I showed you guys before. Right in there. So we now have done all the computation to show this everywhere in the world, right? Whereas 10 years ago, we couldn't say that. This is published 5 years ago, 6 years ago. So now we can look at models that actually have that upper part of that thermoboundary layer getting entrained and acting as a buffer around what essentially is a Loa side of a plume and the a.k.a. side of the plume that must come up side by side, right? And when they come to the base of the crust, they start that interaction with the base of the crust, start that melting process, move through, and erupt on Hawaii Island, on the same island here. Not only that, these guys are also showing that there's a lower path of magma that can kind of stay enriched lower down here. All the stuff up here, this is kind of where it's being tapped to feed, right? So you have some kind of dredges, leftovers kind of still moving underneath this fanned out, dragged out part of the plume. And it's from that you can have these rejuvenated eruptions that can happen many millions of years later. Right? So for example, on Oahu, Diamond Head, Hanama Bay, Coco Head, Coco Crater. The youngest of those eruptions, 70,000 years ago. Some of them is debatedly 30,000 years ago. It doesn't fit with the rest of the island around 3 million years, 2 million years, whatever range for the parts. So that's how you can have this kind of rejuvenation. Not only that, you still have some magma in here, so you kind of take this, you add it up into here, you have some stuff through in here, which maybe means you have some pathways still not quite all the way closed up, and that's how you can have an eruption out of a volcano that's not directly over the hotspot, right? Haleakala volcano on Maui, last eruption 1790, active and dormant. So over here on the right, they kind of show just the Kea side, looking down. This is the surface of the Earth right here, and kind of this is the tongue that's kind of underneath, right? And then the stem of the tongue down over here. And so stuff's coming up and causing various stages of shield volcanism, but then there's some stuff that goes on the underside that rejuvenates coming up, right? And that is something that you see more so the Kea side feeding this early stuff, and you don't really see as much. You see this green signal, right? More of this outer part when it comes up from below to rejuvenate. So when you rejuvenate, you don't see that Kīlauea pattern anymore. It disappears. It's only during this more active young stage of growth. So it's something to do with this core part of the plume. So that's kind of one way to look at it. This is 2013, Hoffman and Farnatani. A different view over here from Petruska is that you might have not only a zonation from Kea to Loa in this direction, but also from younger hotspot to older hotspot. So you can actually have more recycled crust in the actual stuff, in the actual magma chemistry. That can change over time, and you can have more kind of a blobby appearance to it, right? So they might argue that there's more variation going this way than you see going this way. So really, we need to worry about maybe there's separate little blobs that each thing is tapping, and it's more like that. So that is a valid view, and it might be that you have some combination of these blobs coming up, right? But you still have different parts of it where you have a core that's more tapped by a Loa trend, Loihi, Mauna Loa, Hualalai, and then it might be the Kea trend is tapping more of an edge of it for Kilauea, Mauna Kea, and further up. So a lot of unknowns. It's amazing that we have come this far just based off earthquakes and chemistry of lava rocks and dragging, stuff across the ocean floor. So kind of show one last thing here to kind of tease some more of these ideas, right? So we have on here drawn a helium map of the plume. So you can kind of see that it does come up underneath the south part of Hawaii Island. It's kind of dragged off to the northwest over here. So that's going to have to be that zone of the most interaction, right? The depth to the moho, this is the boundary between that crust and upper mantle, which are both solid. You can kind of see that it's a little bit shallower here. I think it goes a little bit deeper there, and a little bit deeper there, and a little bit deeper there. Right? So you kind of show that there's like a deepening of the moho, but then also a shallowing of the lithosphere happening. There's kind of a weird pattern happening with a plume interacting at the bottom of the plate there. If you look kind of closely, you actually have two different lineations. You look at Oahu and Molokai, this angle of motion is different from what appears to be a current angle of motion, even in the last million years or so, a couple million years, right in here. And so they've actually done a little exercise saying, okay, well, actually, maybe we have a hotspot moving again. And so we have combined motion of this, which is actually, we see that plate motion there, and maybe the hotspot is, once again, doing a little jiggle back in this direction, and that might not be that's surprising now that we've discussed how the hotspot used to move, and maybe it stopped moving, but maybe it's not, didn't stop moving, it's still wiggling around. That's kind of in the details we haven't quite uncovered yet. So, so that is the angles, the plume, and the current, some of the current questions we still have left there. All right, so I think that'll finish it for us, and we'll take some questions here shortly, but kind of to wrap it up, you kind of see that we have these slabs that are sinking down, accumulating against the core of the Earth, generating some of these plumes possibly coming up, right? But also possibly blocking flow in some areas. So we've often thought about the slabs maybe being the drivers of tectonics, especially when you think about this as dense weight kind of pulling down. That's what actually can pull the spreading ridges apart and cause mantle to kind of come up and repave the ocean floors. That might be more of the slabs kind of pulling down, but once it actually goes and hits the core and reacts with the core, it starts coming up as a plume, then you have these other features, right? You actually have deformation of the whole geoid over here, once again, is being mentioned, right? And it may be that inside of the Earth, we have so many plumes that it turns out that if we take out everything else, it might look something like this. So what's really driving the Earth there? Is it the plume? Is it the slabs? Or really obviously some combination of both, but kind of interesting to think of what a big part the plumes actually have in the whole movement of the Earth. And all that is connected here to Hawaii. And so in a few places you actually can get this tapped heat from the core of the Earth kind of coming all the way out to the surface through this long process that's taken 100 million years, and tectonic plates moving all over the place back and forth. All right, Dane.
All right. Nice session there. That was a little longer one than we're used to, but really good information, lots of stuff to go through. Yeah,
something where I didn't want to. I knew the questions would be there, and I didn't want to kind of do it halfway either. So it did take a little longer, right. And that's kind of why we got a little later start. And apologies for that.
All right. Well, we got a bunch of questions set up here. Try not to go too long on them. We are pushing the 2-hour mark already.
All right.
But we have some good ones, so we should just, get through some of these. Our moderator, Marin Purvis from Hawaii Tracker, asks, how can you tell the difference between the P and S waves in the seismic?
It's kind of the amplitude and the duration is the easiest way to tell. It's hard. Without being a seismologist myself, kind of just trying to recap, right? I mean, there's the P wave is more of that initial jolt that you get, right? And then the S wave is that after a little delay, the more higher amplitude shaking. So if you see seismograph and you see like a small little jolt and like a smaller wiggle and then a bigger wiggle, the bigger wiggle is the S wave, right? With the caveat that the surface waves also have bigger wiggles. And if you're really close to the earthquake, they can kind of all come one on the other. You might see them all stacked together. But if you're far away, you might see the P wave, then a higher amplitude S wave, and then it kind of attenuate, then a surface wave with also higher amplitude, but also longer, like kind of more drawn out.
Right. Before we dive into the next question, we do have 2 super chats I need to mention, and I believe one donation on Hawaii Tracker. Nancy Knight says thank you for $10 super chat on YouTube. And where is it? Jeff Williams, $5 super chat. He says epic. And then we also had a donation on the Daphne F and Kit K and Brian B. I'm not sure if I mentioned that one earlier, but those are new donations on hawaiitracker.com/support. So we appreciate all you guys. Thank you. And with that, we have some more questions to get into. All right. So do large, Alexander asks, do large swaths of the Earth's crust dive under the sea or land from time to time?
Yeah, it's doing that constantly, right? So if I go back to, I might have to pull up my my geologic plate map. Let me find one of them over here and put it on the screen. So maybe the tectonic map is better. Plate boundary map. So in this plate boundary map, wherever you see these little black triangles, little teeth mark, that's where some plate is getting consumed. So the way it works is the teeth are always on the upper overriding plate, and the other one is the one going under. So the Nazca plate's the one going underneath South America there, right? And the Cocos plate is going underneath Central America, right in here. You got this Juan de Fuca plate over here going under North America, which is actually the very last tail. These two are the tail coats of the larger Farallon plate, which is one of those blobs that's still underneath North America over here. You saw in the imaging thing, yeah. So yeah, there are large swaths, like that whole area is going back into the Earth. That whole area is back into Earth. That little one in North America, but all the Aleutians. You got the Philippines, have the double arc over there. You get all over here, Java and Indonesia, Borneo, and kind of this whole area north of New Zealand, right? Not to mention the giant crash between Eurasia and Africa and India over here, right? Where in that case, they're not so much, when you don't have any ocean crust, and this is just two continental crusts, they stack on each other and end up building really, really high mountains. So that gives you things like the Himalayas and the Alps and, Iran and all that stuff.
All right. We have a 100 Czech koruna donation or super chat. I believe that's about $5 USD. I'm not exactly sure on exchange rates. But yes, thank you very much. He says, thanks for this awesome stream. And this next one, I like this one because I've wondered this one myself. Paul Johnson asks, are Mauna Loa and Mauna Kea at about the maximum elevation for a hotspot volcano since the plates slide away before it get much bigger?
Yeah, I believe so. I think that's the general thinking, is that if Mauna Loa is today at the highest point in production of eruption rate that we've seen throughout the entire hotspot chain, and it's that high, and Mauna Kea is that high also, and then we see all these giant landslides off the side of Mauna Loa, that's probably as high as it gets because it keeps falling apart otherwise. Yeah, right. So that's just best educated guess. But yeah, I would agree.
This is a follow-up. I'm not sure who posted this one. Once off the hotspot, will the Big Island at least partially sink down into the crust due to the pressure?
So the islands go through an interesting effect, right? They do kind of sink, but they also cool and contract. But also that kind of buoyant layer underneath them disappears, and the crust that they're riding on is changing as well. So, but the effect that we do see is that the islands do kind of sink and are eroded at the same time. So you actually have material, new material of the islands of the volcanoes getting exposed because it's kind of, as you erode at the top off, it's like shaving like an ice block that's floating in water, right? If you shave the top off, you eventually will reduce how much ice you have, but you'll take away some of the ice, but the ice will just rise to meet, and you'll end up not lowering as much as you shaved off, right? So it kind of has that kind of effect as well. So yeah, it's interesting. It should cool, contract, sink, be eroded, and actually exposed all at the same time.
Right.
Yeah, what pattern we see.
It looks like we had another donation on Hawaii Tracker. Thank you again, Diana N. Going into the next question. Sorry, I just lost it. There we go. So, Sura asks or points out that the bend in the chain and the archipelago seems to resemble the west coast of the United States. Is there any correlation or connection to that?
No. Well, I think that's just kind of a coincidence. There's also distortion from, really we're on a sphere and it's hard to plot and look at a sphere. So, there's some, it's hard to say exactly how it does match up. But yeah, when I did show that kind of original superimposition of the whole Hawaiian-Emperor chain with the continent of North America, does kind of match up pretty nice, doesn't it?
Yeah. I mean, close enough considering when you're looking at Pangea and some of the, like, oh, this puzzle piece fits here. It's like, oh, kind of sloppy, but okay. But yeah, I can see that for sure what they're coming after, pointing that out.
Yeah.
So Saskactus asks, do we know if Kilauea's plumbing is connected to Mauna Loa? And if so, at what type of depth?
So they're not connected. They have separate feeders, and that is shown by the different lava chemistry. Right? When we have an image like this, we can measure the chemistry of the lava rocks at Kilauea, and they're different from the ones at Mauna Loa. So Mauna Loa's got a separate feeder from this hotspot zone interacting with the lower crust over here. Lower crust and upper mantle lithosphere area. So probably some melting's happening there, and then some of that stuff's coming up and through as well.
One of the things that you pointed out there that was interesting to me was from one of the previous answers, is when the island moves off the hotspot, and it's really represented kind of well in this image, even if it's unintentional. It moves off the hotspot, you lose that little bit of inflation uplift from the magma coming in, so you then deflate naturally or compresses, settles on top of itself there. And I think that image there actually showcases that kind of well. Just like that propping up, that extra little bit. Dorothy made a $25 super chat, or $24.99 super chat. Very informative chat. Great job. Thank you, Dorothy. All right. So, do we know, or Jenny asks, is there a similar plume under Mount St. Helens?
So
to
no,
the one that we have in Hawaii.
No, Mount St. Helens is that other kind of volcano. So we are essentially this hotspot situation over here, kind of coming up through the crust that's moving like despite the hotspot, right? Kind of independently of it, mostly. And what we have somewhere like St. Helens is what we have a convergent boundary, something like this. So St. Helens is one of these kind of volcanoes. This is our stratovolcanoes we discussed in the past. Or what you actually have is you have the oceanic crust going underneath the continent in that case, and it's diving down. And it's because actually mostly you have all kinds of interactions with water on this upper part of the crust over here. And when you bring that water down in here and you add water to the bottom of this continental crust, you can lower the melting point and you can induce melting in a certain region of this root of the continent. And it's from that that you derive magmas that are higher silica composition and erupt out of the continent, and erupt in long arcs, kind of possibly multiples at a time, right? Not necessarily like at once, but in geologic time. Whereas in the Hawaiian chain, only the one at the bottom is erupting, and none of the other ones, right? Our volcanoes are all clustered in one spot over here. I should try over here. They're all clustered in one spot. And none of the other stuff over here is actually erupting, right? Different along a subducting boundary. You might have one over here, and then 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 one over here. You might go in any kind of pattern, but the whole, essentially geologically, the entire margin is active at once, and this is those areas where large swaths of the ocean crust are getting pulled back, recycled back into the mantle of the earth.
All right. Freeman Bashir asks, does the Loa and Kea lava trends have the same north-south magnetic orientation in them? Yes.
Yeah. That's more related on a time of eruption rather than because they both have the iron. Yeah.
At the same time, yeah. We do have one more playing into that. Oscar asked if the Loihi Seamount is playing into the Loa and Kea trends and the overarching curve.
Yeah. So. The Loihi is thought to be on this Loa trend, right? The Loa trend that's over there. But it's also at this kind of youngest part of the plume head. So it probably gets the freshest stuff. If we look at the kind of this diagram, it's kind of the very outermost first stuff that comes up is the stuff feeding Loihi. Right? So it's kind of in that initial stage right over there.
Right. I'm just making sure we get some of these.
Yeah, I mean, just one more thing. I mean, here's that chemistry plot. Loihi is on here on this Mauna Loa trend, right? Here's Loihi and Mauna Loa, so it does fit in that pattern. Last eruption 96, in case that didn't come across.
One of the questions we have is on YouTube is about the time frame of the bend that we were talking about. What years that it was taking place? They're asking for astronomical impacts associated. So the biggest one that we know of around then would be 65 million years ago.
Yeah.
Outside of that, it gets kind of gray and gets big gaps on knowing where these things are and when.
Yeah, for sure. Yeah, and that's something that was considered. Like there are, if I go back to, let me find my large igneous province map over here. Right, there are some times when you look at some areas got giant eruptions of lava and you don't see any hotspot anywhere near it, and you're like, well, what's going on there? So there could be things like asteroid impacts that could cause big eruptions, possibly, whether it's right where they hit or antipodally, like across and opposite to Earth, where all the energy tries to shoot back out. So I mean that's hard to really know, but it certainly is possible. I hope that I've shown you guys, through the imaging that I personally now favor more the deep source of all this action, right? Coming from deep in the core of the Earth rather than coming from outside of the Earth. Although, interestingly, a lot of those stellar body impacts are from other planet cores and pieces of other similar stories like that.
All right. Looks like we had one last donation on Hawaii Tracker /support by Julie F. Appreciate it. And I believe that actually gets us through most of the questions right here with that one. There's some really good questions. A lot of people appreciate this presentation. Some of them were like, it feels like you're doing a PhD dissertation and trying to cram it into a Zoom or something in 1 hour.
Yeah, I figure that probably no one will take all of it away if everyone takes just one little bit of it away or has some interest or whatever else. Like, there's a lot of, I'm trying to expose you guys to the themes here, right? But, I certainly have not been exhaustive or covered everything that there is. I've kind of just tried to, it's a big question to answer. Like, what is the hotspot? And that's why I've always been like, oh, we'll talk about that later, or that's some other time, because it takes this right. Kind of, to me, to satisfy the questions that I have, like, well, but then what? But then what? But then what? You have to go through all the entire sequence of events there.
Right. You almost want. I'm surprised you didn't take it all the way back to the Big Bang. Start there. No, just
try to keep it under 12 hours, right?
Right. Well, I think that does it. Appreciate everybody. We are brought to you by Hawaii Tracker, hawaiitracker.com. Check it out. Maybe make an account. We're really trying to get this thing going, a community-based social media platform where community comes first. All right, Phil, good job tonight.
Yeah, thank you guys. Thanks for all the good questions. Yeah, you can. We'll try to catch up on all the questions in the chat. If there is something more technical, I'll try to get on there and at least put down some references for some of the stuff that's on here if you guys didn't catch it from the video. So mahalo, you guys, for tuning in, for sticking with us for our long presentation tonight. We're not going to do this that often, and, kind of this one shot deal here for this topic. And we'll be back with our regular catch up on the volcano updates on Friday, and we will see you then from Hawaii Tracker. On behalf of Dan DuPont, I'm Philip Ong.